Hey guys, welcome back. In our previous video, in our part 1 video, we have understood what exactly is mobility. And in this video, we're going to discuss about mobility enhancement and we are going to introduce the concept of strained silicon. So why on earth are we discussing this topic? Let's understand that first and we will go to strained silicon later. First of all, we want to make our chips faster and faster. The computing speed has to increase with our newer and better chips, right? In order to increase the speed of the chip, what we need to increase is the current or the drive strength that the transistors can handle. Now, ID equation says ID is equal to half mu n Cox W by L VGS minus VTH whole square. This is the most used equation. How to increase this ID? With increasing ID, we will increase the speed of the chip. We can increase any one of these parameters like mu n or Cox or W or decrease L, which we are doing it by scaling down the transistors VGS minus VTH, VGS or VTH. By fine tuning any one of these parameters, we can make this ID increase. Now, W and L are design parameters, so as the VGS and VTH. We have understood and discussed in our previous videos how to increase Cox and why high K and low K dielectrics are used in advanced technology nodes. So finally one thing is left, which is mu n, which is the mobility of either electron or hole. We increase the mobility, we increase drive strength, which in turn increases the speed of performance of the chip. So from our previous discussion, we have understood that mobility is not only a function of temperature, it's also a function of crystal structure. So if we can make some changes to the temperature of the device or the crystal structure or crystal stress of the device, we can make mobility increase. Now, controlling the temperature is not that good. The foundries nowadays go for the second technique, which is the crystal stress. Okay, so what they try to do is, if we can increase the distance between the interatomic distance, we can somehow make the mobility higher, because we can increase the mean free path of the charge carriers present in the channel, which will in turn increase the mobility because it feels lower resistance for its movement, right? And how on earth are we going to do that? So somehow we need to create some kind of physical force as the crystal is growing. We need something like this. Okay, the silicon is there. If you can see these atoms of silicon, we somehow want to stretch these atoms either vertically or horizontally. We want to widen this crystal structure. The interatomic distance between these two atoms should be increased either horizontally or vertically. Now, to do that, we need the same crystal structure as that of the silicon, but wider interatomic distance, and that can be done only with the germanium. So germanium is highly used, and silicon germanium are grown as epitaxy layers. So while the silicon is growing, we need to create this stress which controls the interatomic distance. Now let's understand what happens when we try to make silicon germanium alloy, right? How we can increase the interatomic distance. If we dope germanium along with the silicon, what happens is germanium has wider crystal lattice. So it has to adjust at the interface between silicon and germanium so as to grow properly, right? And that's where germanium tries to stick to the silicon's width. This is only when the silicon is thicker. If the silicon is thicker and the germanium is thinner, then only the germanium gets this compressive strain. So there is a strain here. This compressive strain, what it does is it expands germanium vertically, right? So this is what is going to happen when silicon is thicker. When silicon is thinner and the germanium is thicker, then what is going to happen is this silicon itself will expand and it will feel the tensile strain. So there are two types of strain which we can see, the compressive strain and the tensile strain. In foundry, for PFET, compressive strain is highly used, and for NFETs, tensile strain is highly used. With any of these techniques, you can understand that the electrons or holes can pass through pretty easily. In fact, the foundries and the integrated device manufacturers today are using these two techniques. One is the epitaxial growth of silicon germanium, as I shown just before, in source drain recesses, and the second way is to use a contact etch stop layer or CELS or liners on top of gate. From this figure, we can clearly see that how the strain is created actually. So there is a cavity over here. We can see this white region is the diffusion region in fact, but what happens is an epitaxial layer of silicon germanium is grown over here. As you can see in this cavity, a cavity is made and epitaxial layer of silicon germanium is grown here. This is the alloy of silicon germanium, and this introduces this compressive strain which will increase the mobility. And this cavity, the depth of this cavity, as you can see, this the recess depth, this depth of this cavity is highly proportional to the mobility. As you increase the depth, mobility increases rapidly. This is for PFET both, and there is a compressive nitride layer, silicon nitride, which will also introduce the compressive strain. But in case of NMOS, the strain is not compressive strain, it is the tensile strain. And also you can see that in this figure, the shallow trench isolation, the isolation between the two transistors, this also introduces some amount of strain to the MOSFETs, which we haven't discussed, but this is also a considerable amount of strain which will be introduced. So these are the liners which I was talking about, the tensile nitride layer and the contact nitride, sorry, the compressive nitride layer are the layers which are used as contact etch stop layer. This is basically the CLS is a layer of manufacturing layer where it will stop, it will prevent the etching of the gate, right, during the metal deposition. So I hope you understood what exactly the strain engineering and how it is achieved. So you'll understand what is the significance of the mobility enhancement. This is the statement that comes from one of the R&D members of the TSMC. He says the free carrier mobility in the vertical fin is adversely impacted for very small fin thickness. The TSMC has introduced silicon germanium for PFET at N5 technology. This is 5 nanometer technology node to improve mobility. Strain engineering continues to be a crucial aspect of FinFET fabrication as well. And it's not just FinFET fabrication, it's going towards the nanowires and nanosheets. We have heard that the Samsung Foundry, the IBM, Intel, also TSMC have introduced this concept of nanowires or nanosheets or ribbon FET or whatever they call it. It's basically the gate all around. That kind of transistor technology has really bad mobility compared to that of our FinFET. As you can see in this figure, electron mobility increases compared to that of the FinFET. Definitely, there is no problem with that. But if you can see with the nanosheet PFET, it decreases significantly. There's a huge difference between the whole mobility from the previous generation. So it's important that the strain engineering in nanosheet technology has to be used, be it in 2 nanometer technology or 3 nanometer technology or the 20 angstrom technology of Intel. The reason why I'm saying it is a complicated and fine-tuned procedure is because if we miss a little bit, if the process is not so controlled, it could lead to crystal defects. So I would like to end this video giving you two final notes: that today's designs must deal not only with the partial randomness of the mobility, but also with the stress-induced leakage, which can be devastating to a device. And improper design rules and poor stress engineering can lead to reduced mobility and increased leakage. Thanks a lot for watching, and I'll see you in the next video with another topic. And please do subscribe to my channel, and bye bye.